Okay, so we're going to finish this section 8.5 by talking about the mean of a continuous random variable. Mean is kind of an overloaded word in probability and statistics. And when we think about mean, we want to think of center, right? A measure of where the average, where the majority of some distribution is. And so it turns out that there's some cool connection here with a topic that we've already seen in this course. And we'll see how that makes sense when we see another name for this quantity. So when we talk about the mean or the expectation of a continuous random variable, what we're doing is we're generalizing the notion of average. And a very specific kind of average. We'll start with the idea for the discrete random variables. Okay, so for x being a discrete random variable, by discrete we mean that we can count off the set of outcomes with a probability mass function, so the equivalent of probability density function. So we have this function over a finite set. In this case, we're going to talk about finite, but we could generalize it to infinite and still be discrete. That's beyond the scope of this course. Outcomes, x sub naught, x sub 1, x sub n. So really what we want to think about is these are the outcomes that we could attain, right? So the outcomes, it could be something like specific states. As simple as you want to think about this, coin flips also will fit into this category. The expected value or expectation or mean of x is denoted mu, the Greek letter mu, and it's the sum of all these sum products, or all the products x sub I times f of x sub I. The way you want to think about it is because f of x is the probability mass, it's representing the probability of each outcome. So we're actually weighing each outcome by its likelihood, multiplying them together to get a weighted sum of outcomes, and then adding those together. So for a continuous random variable, this generalizes to the integral over the support, so from negative infinity to infinity, of x, f of x dx, where f of x here is now the PDF. And now we can talk about what kind of integral this looks like. This looks like when we talked about in 8.2. So shout out to 8.2. When we talked about center of mass and moments. Because it turns out that we can also call this the first central moment of x. So we are measuring a moment of x, and so what you want to think about is if the distribution looks like, I don't know, this for instance, then the mean is like the location of the centroid along the x-axis. Hence the notation x bar for sample mean. It's all connected. It's all super cool. But in essence, yeah. So it's the x coordinate of the centroid of the distribution if we think about it as a planar lamina. Crazy, huh? How it all connects. So let's see an example. Okay, so we're going to let f of x be this function, piecewise, k times 3x minus x squared, for x between 0 and 3 inclusive and 0 otherwise. So if x is less than 0, it's 0. X is greater than 3, f is 0. So first of all, A. For what values, it could be multiple, of k is this a PDF? So all we need to worry about is, since f of x is 0 outside of the interval from 0 to 3, we just need to find k such that the integral of the PDF from 0 to 3 is equal to 1, okay? And so what we can do here is we can factor out the k and perform the integral. At the end, we're going to get a k times some number equals 1, and we'll divide 1 by that number, and that'll give us k. So here we have 3x squared over 2 minus x cubed over 3 from 0 to 3. And then if we evaluate at 3 and 0, 0 contributes nothing, so we actually end up with k times 3 times 9 over 2 minus 27 over 3 equals 1. If we combine these fractions appropriately, then we get k times 27 over 6 equals 1, or k equals 6 over 27. And if we simplify that, we get k equals 2/9. So that's the value k that makes this a valid PDF. All right. B, find the mean of x having this PDF. And in the definition, we go out to negative infinity and infinity, but again, we don't have to. All we have to do is perform the calculation over the range of intervals for which the function is non-zero. That's called the support. So we're going to perform this calculation, okay? We're finding the central moment of the random variable. So that's going to be x times 2/9. We need to use that k now. And then the only rub here is that there's a new x factor. So when we integrate this, it's not going to be the same antiderivative. So if you distribute that x and then integrate, you end up with this antiderivative evaluated at 3 and 0. Again, 0 contributes nothing. So 2/9 times 27 minus 81 over 4. If you do the fraction arithmetic here, you end up with 2/9 times 27 over 4. And that reduces down to 3/2, okay? Which means that the centroid for the planar lamina defined by the PDF here looks like, or it has a hinge point at 3/2, which is kind of cool. And so if we wanted to graph this, right, so notice that that's a parabola. And then, but we won't get into that right now. You can play around with that if you'd like. But this is actually where we end our chapter. We're not going to talk about any more applications. If you're interested in this, please do let me know. I can direct you to all sorts of fun and interesting resources. If you're interested in finding out more about probability and how it relates to statistics, I can recommend my book, but if you've taken Stat 300, then you've seen that. But I also recommend Probability and Statistics by Discrete and Shervish. It's a fantastic little higher level intro to probability and statistics that requires some knowledge of calculus. So you at this point could take this, read through this book and start learning about some of these cool ideas. But but let me know.